Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my great pleasure to have Professor Yuhan Hu visit us today. I don't know who is the same last name as the chairman of China.
Thank you.
So there's a famous joke. George Bush asked Condoleezza Rice, who is China's president? New president. She answered, who? Who is who? It's who. But Professor Hu is much more famous than President Hu in the ROC community. He's very active. He's a fellow of ROC, and recently he's a technical committee chair of multimedia signal processing. And he has done a lot of work in various areas in multimedia signal processing, sensor network, parallel processing, very large scale chip design, a lot of areas. But today he will talk about face recognition. Yeah.
Thank you. Actually, Dr. Zhen's joke is actually reality. I received a phone call with a secretary just basically asked, who is this? So I pick up phone the other end and say, who is this? My answer is, this is who? And this go on for about 30 seconds until the secretary start apologize and realize she is actually talking to who. Anyway, today's I want to report some of the fresh preliminary results of our project on face recognition. This is a collaboration between myself and Professor Nigel Boston from the Math Department, Professor Charles Dyer from the Computer Science Department, and we have graduate student Wei-Yang Lin, Ryan Wang, and Gordon Gu from the Computer Science and ECE Department. This is a project currently sponsored by the National Science Foundation. And this is a short agenda. I would like to basically introduce what is the human face recognition problem, because when people are talking about face recognition, my student actually asked, how about the dog face or the cat face? Basically, we think that that's the next step. Not now. It's too difficult so far. We talk about some of the recent progress and the findings, and actually try to stimulate interest in this area. Basically, our group's research so far focused on a new set of invariant, which is invariant to the transformations. And we adopt a new systematic method to develop invariant feature. I think that's something very interesting. We have learned that there is a face recognition grand challenge going on since 2004-05, and we participate a little bit late, starting the last August. And interestingly, that we applied our methodology, and we have observed some very, very encouraging results, which we will report next week in Washington, D.C. during 2006 FRGC workshop. And some of these results I report here is as late as last Saturday, and I also have some number. I don't even have a chance to put it in here. Actually, I received this morning at 8:30. So this is a fresh, hot result, just like a breakfast.
So FRGC face recognition?
Grand challenge. FRGC.
So that's like a evaluation?
It's actually sponsored by NIST, National Institute of Standard Technology. And it's different from the face recognition vendor test, which is actually ongoing. 2006 test is ongoing right now. The vendor test is actually for more matured product, and since we're doing research, we're not there yet. So we didn't participate in the vendor test, although we know it's going on.
Same style as other kind of list evaluation?
It's somewhat different from the vendor test. The vendor test is actually, this year, they actually have a very special requirement that you do not submit a result. You submit your program. They will run on their platform and tell you the result. So just making sure that everything is fair and they can actually time it and the timing can be compared. So there, the development effort is much greater, and we do not have enough manpower to do that. So this is more for research. And this is the face recognition problem. Essentially, in general, this is one of the many possible problem settings. In general, you have a set of gallery photos, and you are presented with a particular probe photo. This is, by the way, this is my youngest daughter. I think that she looks great, so I'll put it here. And then what you want to do is try to recognize, which one out of this this gallery photo is actually the same person as the probe photo, and therefore from the gallery photo where you have the database or metadata, you know who is this person. Okay, so this is one of the formulation of face recognition problem. There could be many other identification problems or verification problems or the recognition problem settings.
So you also detect whether the probe is there or not in the text.
It's not. In this case, we assume it's there. We do not have the detection component. In other words, when we do the classification of face recognition, we do not have this additional class label called unknown or not here. We could have there, but so far we haven't done that yet. So that's why I say our results are very preliminary, but very encouraging.
So you distinguish that problem as an identification problem rather than verification problem.
Right. That's the case. Yes. Okay, so let's see. This is basically trying to ask the question that, when we talk about human face recognition problem, you always ask, how does human compare with machine? And these curves are some of the vendor tests in 1999, 2001, 2003 organized by NIST. And this graph is a false non-match rate, false match rate, which means that if you are on this corner, that means the best performance. And here are worst performance. And the curves are machine-obtained results, and these dots are the individual subjects. In this paper, they report they have some individual subject working on the same set of data and try to see how they perform. I don't know why they try to separate male and female, which doesn't really make too much sense to me, but I claim that in this experiment, the male is doing better. Okay. Pardon? Yeah, that's right. You're right. Thank you. I think this is a good explanation. But in general, that human beings are still doing better, at least from the 2003 situation, than the machine automated face recognition. So this is the state of art. Doesn't mean this is a 2005 or 2006, but this is just a reference point we can take a look at. This is actually from Professor Pawan Sinha's website, but I think this is very nice. That actually, so I basically, you can go to this. I think the PowerPoint is available for the audience if they want, right? The PowerPoint file. Yeah, so you can actually go to the website, download the original paper, and actually get this figure. I like to show this to my student. My student always want to see this. Essentially, you try to recognize this. How does this figure created? This is created by identikit artist, who is an artist in the police station. When the witness report that how the suspect looks, and they try to, based on the description, produce a composite face. Like a John Doe, Jane Doe, or whatever. And in this experiment, Professor Sinha had this celebrity's face picture put in front of the identikit's expert and asked them to do their best to produce identikit's composite face, which looks similar to the celebrities. Okay, and this is the result. I just want to ask, can you recognize any one of them as a celebrity? Who is this?
Is this like Washington? Denzel Washington?
No, it's not Denzel Washington. It's Bill Cosby.
Oh, Bill Cosby.
Oh yeah, that's right. This is good. This one?
Clinton.
No, but he's a president. Ronald Reagan.
Oh, it's Reagan? That doesn't look like Reagan.
And this one?
That's the guy who plays Star Wars, right? That's the guy.
Star Wars?
No, he looks like a basketball.
And all right, Michael Jordan. Well, this example is to illustrate that our capability to recreate the perceptual similarity of human face is rather limited. Of course, that also means that next time if you're unlucky being picked up by police because you are similar to some famous person, don't be surprised, because we're not there yet. Technology is not there yet. Okay, so this is actually.
Are you saying we should print out this PowerPoint presentation if we get pulled over?
Maybe that's the case, yes. Or you'll be, they think that, oh, hey, Tom Cruise, give me signatures, right? You can help that. And these are some other challenges that illustrating that, what the current automatic face recognition system would face. The first problem is, this of course, I don't want to say what it is, but you know what it is, right? But these are the actual pictures which captured by the monitoring system. And based on this, what do you want to recognize? That's the question, right? This is an unrestricted situation. What can you do with this picture? Right? And on the other hand, human eyes, human perceptions are very good. That's why if you're very close, you don't really see anything. But if at your position, or maybe from the camera's position, you know exactly who this person is. If it's, assuming it's a celebrity, right? Yeah, sure, Einstein, of course. But if you look this close, you won't be able to see it. So you see that our human mind, our human brain play a lot of tricks. And we still don't know how to play those tricks in our face recognition algorithm. That's basically so. And of course, this one is, if it's a celebrity, then even at this kind of resolution, you can do a pretty good job. I'm sure everyone can recognize almost everyone. But if you put your own algorithm to these things, okay, it got to be performed very miserably, right? Think about it. Think about any algorithm, for example, eigenface or whatever. And that basically means that our human mind, especially with respect to familiar subject, then we can play a lot of tricks. On the other hand, I didn't put over here, if we're faced with unfamiliar subject, then our human face recognition performance probably will not be as good as even the current automatic face recognition. You may ask why we need the automatic face recognition other than the security purposes. I can think of many good things. In the classroom, professor face thousands of hundreds of students in a big classroom. If I have a good face recognition software, on my camera on my eyeglasses, when students raise their hands, then their names automatically print out, right? I can call them on the first name basis. The candidate campaign, political campaign, you shake hands, everyone on the first name basis. And you can actually say, how's your dog, Millie or whatever. Isn't that so? The face recognition has a lot of positive social value if you do it right. Of course, you can have someone give you this who recognizes everyone and try to tell you who is this person. But if your database, personal wearable computer can facilitate those things, everyone can be governor, if not president, right? At least can run for it as just like a politician. So there's a lot of good things you can do with the face recognition. So now there's some less interesting part. We're looking into the machine face recognition method, and that actually is the plain old pattern classification. Right? You basically have pre-processing with the input. You're trying to do feature extraction into pattern classification. So not very excited. And well, these are some of the steps, just to reiterate it. This happened to be the graduate student. You have a query image, you do feature extraction, and then you do pattern classification, and the result, you see who is this. However, for the current machine-based face recognition, it suffers from an important challenge, which is called variations, feature variations. This is example of feature variation. This is actually an example of a pose-oriented feature variation. In this paper, Professor Sinha claimed that if you use a simple pixel-by-pixel difference as your similarity measure of how the two faces are similar, then most likely that these two faces, these two pictures, we assume to be somewhat similar than the first and the last faces, right? If you just do the pixel subtractions. However, in reality, these are actually two different poses of the same person, while this is the other person. And that basically says, pose variation created certain challenges for the current face recognition system. And beyond that, there are also other type of challenges. For example, the lighting, the expression, the facial expression, the distance, the low resolution, and also aging. When you take a picture this beginning of this year, and for example, if I use face recognition, if my gallery picture of me is when I was 30 years old, and then my probe image is now at 50 years. Oops, I'm released. Okay, oh no, don't worry, forget about ages. Now, then, it will be difficult to recognize then that me is this me, right? So these are aging problems. There's many tests over the past on this face recognition. People want to compare what are the results. These are some of the statistics just to summarize, what kind of timing and what kind of number of signatures being used, the complexity of the problems, and these are considered small scale. Okay. And of course, you may ask, what exactly is the scale of face recognition? It depends on, of course, applications, just like other pattern recognition problems. However, if we want to do unrestricted face recognition, for example, you go to the airport, you have a set of 10 most wanted people, putting on in front of this the immigration officers, and then every passenger is passing by. Then they will have to do this face recognition, unrestricted face recognition for every person, try to do this kind of matching things, right? In those cases, then your gallery could be as large, could be rather large. So that could be an issue there. So the face recognition problem, there's all kinds of formulation. I mentioned about face recognition grand challenge, and this is actually started, I think, in 2004, and probably will end around this year. I don't know the future. It has this kind of a problem. It talks about single still image, or this multiple still image, but with a less restricted environment, like the pose variation, lighting variations. Or the complex background, which requires a very intelligent segmentation, first find out where the face is. Or you actually have this three-dimensional range image for face recognition, and it has three-dimensional, the full face. I think the difference is that full face has more of the range image covered. So there are some of the challenges in these things. In our group, we are focusing only on this three-dimensional face recognition, because two-dimensional is a rather crowded field, and we don't have enough manpower to enter everything. So now let's try to go back to this object recognition, and basically try to give up this overview of what kind of approach people have been taking and what is our approach. So we're now try to move into this UW-Madison face recognition group's approaches. In general, there are three types of approach, or sometimes we say two types of approaches. One is, according to Professor Sinha, he says there's transformational approach, view-based approach, and invariant-based approach. The transformational approach really are the pattern classification method where you actually perform normalization. The idea is that you can estimate accurately or relatively accurately the type of variation through certain transformation, and therefore you know the parameter, or you can estimate those transformation parameter, so you just undo the effect of the transformation and normalize the features into sort of a standard feature direction. For example, in character recognition, you want your characters to be standard height and width and so forth. The view-based approach basically say, maybe the variation is not that many, so why don't we just try to remember all the possible variations and then put in my database and then try to do the match. Okay.
In the evaluation database, how much examples do you have in the training?
Not in this one. We use the FRGC things. That basically have I will talk about. There's a multiple instance, but not too many of each individuals. Invariant based in general is that you basically say, oh yeah, if we have an invariant feature invariant to a certain type of transformation, if under the assumption that a feature may only subject to this type of transformation, then we can just go ahead and extract the feature without worrying about normalization. So this approach and this transformation approach are very similar. The only difference is that in this transformation approach, you will have to spend time to estimate the parameter. Once you estimate the parameter, you can undo this transformation. This one, you just basically say, I probably do not need to estimate the parameter. I just directly extract the feature. The end result probably is the same. You just extract the feature of either the normalized or from this invariant feature. Whether it's transform or before or after, you still remain the same feature. So this way, you can actually reduce the variations experienced in your feature space. And of course, in general, you want your feature to be invariant to the variations of the same object. And while at the same time, you wanted to maintain the necessary discriminant power so that you can distinguish similar feature but belong to different subject. So we are focusing on the invariant features. There are several invariant features have been used in literature. For example, there's this moment invariant. It exists since 1962. And there are, of course, also Fourier descriptor invariant. I may not refer to the earliest references, so forgive me that if we're not really finding out the correct history, giving the credit to those authors. There are also wavelength coefficient-based invariant. And of course, there's a lot of people using the geometric invariant to transformation, to the translation, rotation, or even scaling. Okay. There's a lot of people using this differential invariant. They call it curvature. Sometimes they want to make it more robust. They call it Gaussian curvature. And there's quite a few papers. These are just some sample. And in 2002, two mathematicians proposed something called the integral invariant. And our research works are motivated by the development of the integral invariant, and we developed something we call the summation invariant. So this is where our approach relative to the existing approach. And since we have a mathematician in our group, that's how actually our mathematician, Professor Boston, get excited into this area. Okay, let's try to talk about a little bit more about the geometric transformation groups. Of course, there are Euclidean, similarity, affine, projective, and maybe others. That what we're interested in and what we are trying to talk about is that with the geometric transformation group, interesting thing in the geometry is that, algebra I guess, is that there are some method called method of moving friend, and this is a method that allowed us to systematically, important thing is to systematically develop geometrically invariant features. Okay, actually not just one. We can develop a family of invariant features, and by different settings, we have the opportunity to derive different families of invariant features. So this will be an interesting progress in pattern classification in general, because in the past usually you have one invariant feature and then you try to beat it to death. Now we suddenly have a way to allow you to develop your own invariant, put your names after that. And then this actually is a systematic method. You can do a lot of new feature exploration. This gives a lot of opportunity for exploring new invariant features corresponding to different transformation groups. And there are some mathematical derivations which I always find that it's difficult to explain. So I'm going to jump into this in more engineering procedures, algorithms, to talk about what is this method of moving friend. And the idea is like this. I'm going to give a concrete example, so forgive me for the conciseness of this summary. We assume that we're given a transformation, Euclidean, affine, whatever transformation, over a point of a curve in two-dimensional space or a surface in a three-dimensional space. As you can see that these are restricted to some sort of not every two-dimensional, we're not talking about region, we're talking about a curve. In three-dimensional, we're not talking about solid, we're talking about surface. So these are sort of rather restrictive, the subspace in this kind of dimensions, right? What we do is we would define something called potential, which is somewhat like a moment, but it's not exactly, because of our way of of a parameterization of the curve and the surfaces. And then we're going to construct basically a vector space called the prolonged jet space. From there, we solve a set of normalization equations for this for the transformation parameter. You know, transformation rotation angles, the translation offset, and the scaling factors. We're going to estimate those parameters. Then those parameters then will be estimated as a symbolic expression of the origin of the data point on the surfaces. That's important. We substitute those values into the potential of the transformed potential expression, and then the result will be called geometric invariant. And it can be proved using this approach. Those invariants derived before and after this transformation remains unchanged symbolically.
So what's the dimension of the invariant feature of for the regular?
They are actually for a bunch of points you derive one, a bunch of support you derive one scalar for that, and then if you shift those windows you can develop a sequence. For example, if it's a curve, okay, I can put a window, and then for each of the segment of the curve I develop one invariant feature. If I shift that curve by 1 pixel, I can derive the next one. In our cases, if a curve with n point, we actually end up with n features. The feature dimension is the same as original data. In our current implementation, I'm not very satisfied because this actually gives us maybe a feature dimension which is too high. But our time is limited. We have to run the experiment to catch the deadline, so we don't have time to do all those kind of optimization. This is, again, very, very preliminary result.
Can you tell me what do you mean by transformation parameters?
For each feature, you're developing variants.
Okay, what we're trying to say is that, for example, in the post variation, that's what we are focusing right now, I have a three-dimensional surfaces, right? And then I have another three-dimensional facial range image is that I turn my head about 15 degrees, right? So that's the rotation of the points on the surfaces with respect to some center which I may not know, right?
So do you have to construct the 3D model to begin with before you do?
Yes, we assume we're given the range image, which is really a 3D model of the surface. Yes, we are assuming that we're given the 3D surface. When we do not talk about how to get those 3D surface, how to smooth and get the pre-processing of the 3D surface. There's a lot of course, details I won't have time to go over, but this is basically our general approach. Okay. So transformation is really about that if it's a pose, that's basically rotation and those kind of things. And we're not really going to address the lighting, and we are still thinking about what happens facial expression changes, what kind of transformation that corresponds to. We don't know yet. If some of you can tell us, we'll be very, very grateful. That's a difficult problem, mathematical problem. How did you find a mathematical transformation to model your face expression? Changes, like laugh, cry, or eyebrow going up and down, and so forth.
You only look at geometry without looking at the color. You only look at geometry. That's just position change.
Well, not necessarily, because we got a 3D surface. When you smile, your chin's actually, the surface actually, the curvature changes, right?
That's surface deformation. But I thought because I'm looking at your features is point by point anyways. So
right, but it's defined on a segment of surfaces. Each point is defined actually on a surface.
Oh.
It's not just one point to a point.
Okay, so that's
yeah, it's the support for each of the feature, each of the scalar feature. The support is either a line segment, a curved segment, or it's actually a piece, a segment, a piece of the surfaces.
So you need a neighborhood.
Yes, yes, and that size usually should be large enough, because if it's too small, then we actually use it's essentially the same as differential invariant. That's something we like to avoid, actually. Okay. All right, so just basically go very quickly about differential invariant. These are some examples, of differential invariant. And by the way, differential invariant, integral invariant, and the summation invariant we derived, they can all be derived using the same approach, namely the moving frame approach. The difference is that what kind of potential you define Okay, but so the method of moving frame is a very general method for develop geometric invariant. This is just some examples, okay? And what I want to illustrate are these xxx. These are partial derivatives 3 times. And which means what we're trying to make the point is that differential invariant is sensitive to noise because you take so many derivatives and you can derive many different differential invariant, not just curvature. There are many of them. But many of them actually requires high order derivatives, and that is not good. Okay, that's the real issue with the differential invariant, and that's why many of the curvatures are actually not original curvature. They call it Gaussian curvature, and others they do the smoothing, try to reduce this sensitivity. And there's something called also robust or called semi-differential invariant. Some of the methods which try to do some averaging of the curvatures and try to reduce the amount of the dependence on this noise or the variations. Okay, so differential invariant has this inherent problem. It requires higher order derivatives, at least from theoretical point of view. Integral invariant proposed by 2 mathematicians, Han and Hickman in 2002. The essential thing is that they use this integral to define as a potential. And what's important is that under this formulation, the assumption is that the curve, they are doing only the curve cases, 2-dimensional cases, they assume the curve are represented algebraically as a function, as actually implicit function of x and y. So when you have this derivative y dx, x is not the independent variable. It's actually both y and x are a function of a third variable. For example, in a circle, you define x as a cosine theta, y as a sine theta, right? So then x is actually the cosine theta, y is actually sine theta, and the real variable is theta, not this. So this integral is not just like it's not. What I want to say, these are not moments.
So this is really a line integral.
Yes, it's a line integral. It's not a moment. It's integral over the line. Yes.
It's not the curve.
Yeah. So these are the subtle points. That they are implicitly function representation of the curve. So that requires special pre-processing. We have to resample the point along the curve in order to get it right, get the computation right. And this is one example of integral invariant. And this y1, y0, or x1, x0 are, we try to, in this case, we set this normalization equation to be the initial point of the curve and the ending point of the curve to be invariant. So these are the initial and ending point of that curve. And then these i's are defined as the potentials. So you can see this is one of those potential after transformation. And then they're represented as a function of the x and y's of the original curve. It can be proved using this method. This is an invariant to whatever, in this case, I believe is Euclidean transformations. And the advantage is that there's no derivatives there. There's only integral, although it's complicated integral. However, in this formulation, it requires original curve to be represented as an analytical expression. Which means when we implement, we have to approximate and do the proper sampling, and so there could be also numerical integration required. So numerically, there are some of the challenging tasks there. So these are some of the existing work, and what we have done is that the last year we actually worked on this summation invariant as a more robust way of implementing the integral invariant. We define, instead of an integral, we actually do the summation, and we have a way, I will introduce how do we do that in the next few view graphs. And of course, we do not eliminate this limitation that our curve still has to be represent at least analytical, not analytically, but has implicitly represent as an implicit function. In other words, y and x are function of a third independent variable.
So if you do the smoothing over the noise image, that going to help you reduce the problems of sensitivity?
Definitely. If I think that's what Gaussian one of the approach of Gaussian curvature, I believe, is that the low pass filter the image, and then they try to extract curvature. Then they will reduce a lot of the problems of those things. That's of course, yes. So this is the actual illustration of the method of moving frame using this of derivation of a summation invariant over R2 curves. Okay, so these are the example of a transformation, Euclidean transformation. We assume there's a curve x and yn sampled on a curve, and this is after transformation, Euclidean transformation. This is new coordinate. This is the original coordinate. These are transformation parameter theta and a and b. So this is the transformation. So we assume that what we observed is transformed from some normalized original pose. This is the sort of a variation of pose, and so these are the points on the on the curve. On the what called it? Not curve. It's called it's a pose or not pose. It's a contour on the surface. This is what called the profile. That's right, profile. Yeah, we assume that this is a profile line. This is on the original. This is the transformed the points on these profiles. Then these are our definition of potentials. It looks like it is a moment, right? But it is not. The reason it is not is because both x and y, they are not independent variables. They are actually function of a third implicit variable which we didn't see. So this is a subtle point, very subtle point. Our papers got reviewed. The reviewer always thinks this is a moment and think, what's the difference between this and moment-based approach? Then we have to write 1 or 2 pages of explanation of the details. But these, I want to emphasize, these are not moment. Okay, in order to do this, before we actually do these things, we have to resample on the curve. Okay, resample on the curve, sampled in the sampling, uniform sampling on that parameter. For example, if this curve is a circle, we're sample on the uniform sample of theta. And then we have x theta 1, y theta 1, x theta 2, y theta 2. That sampling is different from if you have just a curve, just a circle, and on the Euclidean grid, you just sample on that curve. These are 2 different things. Okay, it's really angles. It's equal angle sampling. Yes.
So is n is your parameter?
Right. This is after the sample. This is basically because it's discrete. So this is actually the parameter of theta 1 and theta 2. So this actually should be say x of theta n. Y of theta n. This is x transformed of theta n, y transformed of theta n. This is actually, yes?
So if you're defining a new class of invariants, the obvious question to ask is it complete and are they independent? I.e., you have some curves which you wish to describe the invariants. So presumably when you have your invariants, knowledge of the transformation parameters should then allow you to completely reconstruct the curve. So are these potentials like a complete and independent basis for reconstruction?
First, if we just one curve, we get 1 point as the invariant, then there's no way that from that point, that invariant value, we can reconstruct entire curve back.
Yeah. So from your whole set of potentials plus the parameters, does that imply the curve, or is there some information loss?
We haven't really addressed that issue. What we do now is that we are doing we basically segment the curve into overlapping segments, and then so we basically, for example, a circle, we do maybe like 30-degree, we calculate one of the invariant, then we shift by say 1 degree and do the same thing again, so we actually have the same number of invariant as the original one. We do not know that whether we can, this is a sort of transform. From the invariant, we should be able to get the thetas, as you can see. But that doesn't mean that, I don't think that means that we can reconstruct original curve unless we know the theta. See, when you calculate the invariant, you do not have to know explicitly what is the theta value, right? If we know the theta value, if we know the A and B, we use transformation approach. We just transform everything, normalize it back, right? This actually is to give us opportunity not to know those values, and we still can do it. Assuming, of course, we know this is actually the only transformation it's subject to. That's a big if, of course. So this is the potential. And what we do is that we actually try to put this into a space. We call it jet space, actually called a prolonged jet space. That has some details, mathematical detail in terms of the dimensionality of the original jet space. And this selection usually in this case is the beginning point, the ending point, and many of those, just keep adding many of those potential we define as higher orders. So this gives us choice of this potential, this jet space gives us a lot of opportunity to design different families of invariant. Then out of these, we will select, in this case, we select the first three, but doesn't have to. We select three of the particular points, and we require them to be invariant. This is sort of a normalization equation. It's sort of like after transformation, no matter what kind of transformation, these things will have rotate back to these positions. It's like if you only look at rotations. And so we require these conditions. By imposing these conditions with this coordinate, we solve the equations of theta and A and B. Three equations, three parameter. And here's the catch. What we want is that we're going to use Mathematica or whatever. What we want is we hope that this expression of theta, A, and B can be represented in closed form solutions of the original point, x and yn. Okay, that is a big if, and that requires some search. So inappropriate choice of these may not yield closed form solution, and then the invariant won't be in closed form, and then it won't be very useful. So there's no guarantee we always have a closed form solution. That part is perhaps the trial and error, the search area, that we really have to rely on the symbolic mathematics package to help us to really resolve this problem. But once we solve that, if we can solve that, what we do is that we substitute those parameters into this expression. Okay, this is the expression of the transformed potential, right? We substitute the solution of theta, A, and B as a function of xn, yn, and x1, y1, and so forth, and also those potentials into this expression. And then we relabel that into this, and this will be our invariant. Okay, so this is the method of moving Fred. So you can see that basically you have to do the clever selection of the normalization equation or the extension of the jet space. And then if you're lucky enough to get a closed form solution of the theta, A, and B, then you can directly substitute into here to get some expression, and simplified, you get this invariant. For example, if we set I equals 1, j equals 0, we end up with this closed form solution as eta 1, 0.
Yeah, what I'm talking about, always thinking of this. Being invariant doesn't mean it's a good feature for pattern recognition.
Exactly.
You can let everything to be 0.
Exactly. So that's why I have that page of two requirements, invariant and the discriminant power.
So how do you integrate this together?
Well, the invariant, our mathematics tell us how to derive invariant feature, and then our research in terms of using empirical approach, we try to find the invariant feature which give us the best discriminant power. So that part we do not have a theory to tell us which one has the most discriminant power. We have to try.
So you don't have a free parameter in this invariant transformation which can be subject to optimization.
No, we don't. There are actually two catches here. One is that we want to find a closed form invariant. Not every setting leads to the closed form solution. Secondly, some of the invariants are better than the others, and we actually have to conduct systematic feature selection approaches to select invariants which are most suitable for our approach, and also subject to reasonable computation requirement. Okay. So yes, you're right on the mark. That these are some of the concerns we have. So the important thing is that using this approach, you can derive systematically a family of invariant in closed form. And actually, several different families if you're lucky enough. And so I'm not saying that we know which feature is the best, but what this provides you are more options for you to choose from. So what you have is that you have a longer menu, and then you can choose from. You can use a systematic search, using spend a lot of a CPU cycle to search. So the contribution here is that we have a method to systematically generate all these possible choices. Give it a try. Whatever problem you have, try it. And if you're lucky enough, this thing will be your new feature. You write a paper, file a patent about it. Okay. By the way, we filed a patent on this invariant already. Okay. So these are the theoretical part. And we actually generalize this to three-dimensional, and there's some of the in the derivation, there are some of the mathematical maneuvers we have to set here and there, because 3-dimensional, 2-dimensional are not really the same. They are something which we have handled. But I just say that we did it. It can be done. We did it. You may ask, we did it for Euclidean transformation, and the students still working on the affine transform and maybe other things. This is a very good way to generate a few master reports. Just teach them, and they will just do the search. Okay, so let's talk about experimentation part, for the last few minutes. Yes? Okay, sure.
So I was wondering if those quantities are invariant and they're sort of resampling.
These quantities, we first, assuming that our representation of the curve has been properly sampled. In other words, they are sampled in the independent parameter space.
Yeah, but once you suppose like pose like this, now
right.
Pose, now you get different image.
Right.
The sampling is implicit, right?
Right.
So in that case, basically, there is really a resampling going on. So I wonder how you have any theoretical analysis on that.
No, we haven't. We are currently using, actually analyze two things. One is that because sampling always has sampling error, right? When we do the resampling, there's always sampling error. We missing point and we do interpolations. We don't know what kind of effect that will appear. And also that we do not know that, how this transformation will affect this resampling. Because, when you transform, when you do using the same resampling ideas, whether that's a proper way to do that, we don't know. So we're using that, but we haven't really conducted analysis of these effects. Thank you for pointing that out. This is an important subject, yes. As I said, face recognition, this is, we're focusing on the 3D images. These are some of the examples of the experiment defined there. There's a simple ones, controlled indoor, multiple images, situation, 3D images, and controlled versus uncontrolled situation. These are some of the target size. I think there are 4,000 pictures, and there's about, I think, 800 or 900 people's subject there. So each subject has varying between 5 to 8, sometimes 8 different poses. And some of the subjects actually have poses with the within the same semester and between within the same year or between different semesters. So they actually take the aging into consideration. And in the version 2, the subject actually will perform imitating 3 different expression. Not really I don't trust their expression because they are not professional actors, but at least they will try to move the facial muscles, so the facial surface will change. Okay. So yes, there are multiple instances of the same subject, and also each subject simultaneously are captured with texture image and the range image. So there's this direct correspondence between a texture image and the range image. And so that it's possible to do the joint texture plus range image recognition. In our current progress, we only do the range image only experiment due to the manpower constraint. Okay.
So now before you go to the experiment, you have to have the modeling easy one. Once you get the feature, so what model do you do? What kind of distribution do you assume?
What we assume is that we have assumed there's a 3D surface. We assume that the face was subject to some the pose variation. That's basically what I assume.
After you do all these feature extraction,
okay.
for each pose, you get a low vector.
Right. Huge vector. Yes.
Once you have that, what do you do?
I'm going to explain that what we do. The good thing about a face recognition grand challenge is that they try to standardize the experimentation reporting. So what they do is that I'm going to explain that they actually provide something called the BEE, Biometric Experimentation Environment, that standardize the procedure so the results are comparable. Okay. That will be the next few of them. But this is some of the experiments that in the BE baseline they have performed. I think that it's from the Notre Dame group. They are contracted to do those kind of comparisons. We are actually working only on this experiment 3S. And in the baseline, they actually provided also result combining this two using feature fusion to do this the final match. Okay. So this is actually the BE, Biometric Experimentation Environment. They provide an image processing box, a bio box which are really doing the feature extraction. And then there's a sub-similarity generations. Essentially what they require is that you have a set of a gallery images. Each of them you extract your feature vector using BioBox. You have this probe image they specified, and you extract this feature vector. So with the feature vector extract from the gallery and the feature vector from the probe image, then they provide multiple choices of similarity measures, like a cosine, like Gaussian, not Gaussian, like the L2 norm, L1 norm, L-inf norm, and also those non-knowns, all kinds of things they provided there for you to choose from, and then we just try all of them and select one which we figure out is best. These features, the result then become a scalar. So every pair of image end up with a scalar, right? And the scalar has to be such a way that, if it's a match, it should be 1, and if it's a mismatch, it should be 0. So this sort of a mapping from 2 vectors to a 0 or 1 classifications. But actually what you get is a number between 0 and 1. And that will form the similarity matrix, because you put the row column of the probe, of the gallery, horizontal column heading become the probe, then you actually form a matrix, right? I'll show you the matrix later on. And then you, of course, normalize this thing so the match is 1 and the mismatch is 0 or some of the match. And based on that, we're generating this ROC curve, receiver operating curve, and using that to...
I'm really surprised that they take... So essentially this evaluation is on feature extraction.
Exactly.
There's no,
they are actually using a distance-based classifier. It's basically standardized into a distance-based classifier.
Is that the main problem with the feature for the facial recognition?
It's just one choice, which...
One line. There's other lines where you...
Right.
So the different tracks, right?
No, this BE is just one approach, that I think that...
Like a speech recognition, right? You extract feature, they give you,
standard,
the standard HMN,
yeah.
and then you actually do it.
Right.
Okay.
The only purpose is to allow people to compare results. Okay, it's not necessary that in reality you want to always use this. Not all the pattern classifier can give you the ROC curve. Remember that? Yeah? Many classifiers give you 1 point on the ROC curve, not a whole ROC. You have to put in this format so you can generate the ROC curve. Okay.
But that's much better way of doing that in terms of...
I'm definitely sure. This is one way that at least people can go there and say, okay, they just basically change their either BioBox or this method, and they plug in here. These are standardized, and so the result, at least you can plot the curve together. So this, this is exactly, this is our approach. What we do is, no, this is not really our approach. This is the baseline approach, as I said. And the fusion here, don't trust them. They really just add them together. Okay, so it's really the standardized, simplest result. I'm not saying that's not good. We're using that too. But this is their result, the baseline result. And if they say 3S, then this part. 3S is this part. 3T is this part. Combined is a 3. They're talking about this part result. Okay. And this is what I said, the matrix, the similarity matrix. If you have a 4,000 in the gallery and the 4,000 in the probe, you have a 16 million entries in that matrix to worry about. Okay, and normalize into 0 and 1. And what is important is that they actually the ordering this subject in a way, they provide this kind of set. They order in a way that if this is a person, then the corresponding the image will be actually on the diagonal. So what happens is that this diagonal item, the screen area are the match, and all the rest off diagonal are mismatch. And so what happens is that getting this matrix, you just grab those things and they are labeled should be matched population, and all the others will be just scalar and a mismatch. And so what that happens, you can just generate this distribution curve, right? Empirical distribution curve, and you just move your threshold, you can actually get this probability of detection and the false alarm rate at a different range, and then allows you to plot this ROC curve. Okay, and in general, they are targeting in this experiment of constant false alarm rate. They say we should actually have do not allow false alarm rate higher than 0.1%. Using that as a number, they are trying to see what are the verification rate, which is really probability of detection. Okay, there are several different experiments. These are baseline results. That in version 1, it's neutral phase, nice pose. even baseline using the standard PCA approach, they can get 98%. But with the variation of the expression and the pose and other things, drop to 53%. This is using both texture as well as range image. Okay, it drops very quickly. Okay, so this is a baseline. And there's one meeting, I believe, in the last year's CVPR or in San Diego. I guess they have a workshop on this. So this year's workshop is separate, but last year they are combined. And there are actually only 5 groups report on this 3S. And we're competing against this category. We're not really competing with other categories. So I want to make it very clear.
So again, 3S with geometry.
Yeah, yes, only shape only.
Shape, only shape.
Yeah. That's range image only, okay? So 3S, yeah. Okay, so these are the reported results, minimum, maximum, and the best result out of the 5 group. It's somewhere like 86, okay? And actually, these results, I'm not sure which curve this corresponds to. So the next one will focus on the 3S. This is what the shape-only performance. And there are 3 reports. You know, in their experiment, they report 3 different situations. All of them are neutral versus neutral phase, or neutral versus non-neutral means there are people expression. So they use this as training, these as testing. So this is all means that training set, testing set are the same. Okay, and this one is a neutral phase as training set, neutral phase as testing set. They are the same, and oh, I'm sorry. These are separate training set and testing set, but they are both from the neutral phase. This one is training set from neutral phase. These are from the expression phases. Training, testing, and this is training equal testing. And you can see that, of course, you know, the last one is most challenging. And from this paper, last year's CVPR, I think they report 86.9, roughly 87% on that number. And from what we know, out of this 5 group, that number is the best last year. Okay. So we can assume in this state of art until June 2005. And so our approach is that we have actually, there's dots. We have many shape areas. We're using some approach which is very similar to ADA Boost. We basically have a smaller regions of the faces. So we have many of the smaller one, and we get a similarity score. And in this case, we have some of the fusion method, and then we get the similarity matrix. So this is our, in general, setup. I'm not elaborating. Basically, we only focus on the 3D shape, and we do not using the 3D invariant feature. We're using actually 2D invariant features. So in each area, we cut these horizontal rows, and each of them is like a sort of local profile line. We generate a set of invariant feature of it.
So does that technique require the self-detection of the face?
This data set provides the manually provided fiducial point of a tip of nose and the center of eyes. Okay, so it's, you know, I have to make it very clear. So we do not have any result in terms of that. You know, what if we do our own detection? That is, of course, in our agenda to do some. You know, when we have more manpower, we're going to do some of those things. Okay, so our algorithm, assuming we know those, and therefore our cutting those face region is very easy. We just basically relative to those points, as we go. And also those face images have been normalized in terms of the same size. Okay, those are provided, you know, by them already, so we're not really doing much of those part either. Okay. At each pixel, we compute 2 curve summation invariant within the specified window regions, and we compute similarity matrix, and we do some simple fusion. So these are the 10 area regions. You know, we don't know whether we should use all 10 of them. We haven't finished our experiment yet. So current result is use all 10 of them. Okay.
So for each box here, you treat this as
a separate region. And I'm going to next one I'll tell you what we do with each box. Okay. Assuming that we have a box of the nose region, what we do is that we count. This is a 3D surface. Okay. In this way, I do this horizontal. I just do the horizontal each of the profile. I calculate the invariant, which is about the same length of it. I just do this horizontal profile, calculate those invariant. So and then I do that for every row. So if I use eta 1, 0, I get this invariant picture. So they are the same size. And of course, I have to deal with the situation about a boundary, and we do what kind of extension and do those kind of details. Okay. But basically, for each of the surface, I will have a chance to select a different invariant, and we empirically select one of them. I couldn't remember exactly which one I select. I think we select 1 or 2 invariant features combined together, okay, to do our test for each of the area. And then we do horizontal one. We also do vertical one. I always think this looks like a lion. I don't know. Human face is similar to lion sort of things. But anyway, so we do a vertical one, horizontal ones, and then we calculate those similarity. And these are some of the results. This is if we use only the best single region result, just one of the region out of the 10. And these are the baseline reported last year in those curves. And so, of course, our curves should be the higher ones. The higher is the better. Okay. This one is, this leftmost part is 10 to the minus 3. That's 0.1% point. So this is where we're looking at. Every curve converges to 1, so that doesn't matter. Okay. So you can see that there are 3 ROC curves. The first curve means that pictures are taken at the same semester, so they are very close. Curve 2 is, I think, the picture are taken at same year, but it's median distance between them. The time of picture 3 is a picture taken at a different semester, maybe even different year. I don't know, but they say different semester. So usually RO3 is the most difficult one. So this is ROC3. This is their ROC3 of the baseline. This is our ROC3 of our result. It's better, I guess. Now we use multiple region, and in this case we use a very simple fusion. We just added all those things together and normalize it. Okay, suddenly that we jump into this 90% ranges. Okay, so it means there are multiple actually helps. And then we just compare the difference between the single and the multiple, and this is the extra performance gain we obtain just simply by using multiple region. Of course, more computations.
So how other side doing the same task?
Pardon?
Other side. How do groups submit the results for that challenge?
This is for this year. So, and the last year, I don't think we have the curves for other groups. We only have the paper reported numbers, and maybe they plot the curve, but we don't have the actual ROC curve points there. We don't have the similarity matrix, let's put it this way.
Last year the result was
86%, right. So that's around here.
Yeah, but in your previous slide, this is only 30. What's 30?
These are baseline results. These are the last year. This is the not submitted result. These results are given when the data is shipped to us. The BE, when it's shipped to us, they provide a baseline using PCA approach. So we can always compare with baseline. Our basic idea is if you're worse than baseline, don't bother publish it, right?
Among other 5 sites, what are other techniques? How do they compare with?
We don't know. No. Last year's, we only have that paper, Melsberg's paper. We roughly know what their approach is. It's actually from his company, I guess. Massage or whatever that name is, the company. So that's last year's result. This year, of course, I'm sure they will even further improve it. So, but this is we got the data from January, after the winter break, after Christmas, and we start working on that. And this is only March, so we're happy that we're making progress. Okay. And this result actually are not the latest result. Latest result at 8:30 this morning, I heard that we have been able to improve this to 91.4% using LDA-based fusion method. Okay. We actually have a way to do the linear weighted fusion. That's right. We have a 10 similarity matrix, right? We want to combine into one similarity matrix. Essentially, it's a vector of a 10 mapped into a vector of 1. So really, what we observe is that that's a basic pattern classification problem. Well, what we want is a linear pattern classifier, and only 2 classes, match or mismatch. So what is the method you use? LDA, of course, right? And so, LDA, the fusion really is a pattern classification problem, at least for this part. If the temporal feature is not really concerned, fusion problem itself is yet another pattern classification problem. If we restrict ourselves to linear pattern classifier, LDA, and that actually should this thing to another 2%.
So the baseline system, you do LDA all the pixel?
No. The baseline system essentially is very simple. They treat this 3D range image just as texture image. And then they apply PCA, and then they do those things, and they add them up, and then they're done. And actually the Notre Dame group, they actually later on do this 10 region based, still they just cut into 10 region. They shoot up very nice results, even with the baseline PCA approach.
So in that case, all the problem with the pose, variation is not taken into account.
They use normalization. The baseline, assuming they know the rotation angles, they actually use that numbers. We do not use that number. They use those numbers. Yes.
How do you decide on the regions? Do they do more harm than good?
I just tell my graduate student, Ryan, I say, cut into different regions, find, and he used his heuristic judgment, touch his own face and try to figure out, oh, these may be important regions. So, yeah, heuristic. I'm sorry, that's just. I think that's just ADA boost, for face detection. It's heuristic. You just basically try and error, and so these may not be the 10 best one. We may have a new way of partitioning it. And we may not need a 10. We haven't really done the feature selection yet. And for each different feature selection, we may have a different weighting. We're just doing the linear weighting so far. We could easily have a non-linear weighting, right? If it's pattern classifier, you can do whatever you want. Support vector machine or whatever. That's the possibility is endless. So we don't know. So these are preliminary results because we can actually shoot up more if we try different methods, possibly. Okay. So this is basically what I want to report, and what I want to say is that the important thing is we have found that a new way of developing systematically invariant, geometrically transformation-based invariant features, and we have demonstrated, at least preliminary, these features can be applied to face recognition tasks, and we have observed interesting, encouraging results. And of course, there's a lot of work waiting for us to further to analyze this approach, to fine-tune this algorithm. So I would expect that there's a lot of busy work ahead of us. Yes?
So on the curve theory report, I remember that you have 3 cases. One is training and testing on the same set. One is
no, we didn't do that. That is basically, I think they have performed a separate test on those data. We did not have that data to work with. So these ROC 1, 2, 3 are not the same as those neutral, O and O, and we didn't put that yet. And that's our to-do list. Yes, you're right. I want to see those kind of curves. And we hope that by next week, when we report that, we could have those curves generated. Graduate students, you cannot just always squeeze their time. They are human beings. You have to encourage sometimes. Be considerate as a professor.
So, presumably there are other biometric experiments going on too. So how are these verification rates compared to, say, retinal scans?
I've heard that, I didn't touch this detailed issue, but the next week's workshop also have it's basically first day is the face recognition, next day is iris. Okay, iris recognition. So I would know the answer next Friday. I would say that for the face recognition grand challenge, the objective is to improve this recognition rate at the 10 to the minus 3 false alarm rate from 80% to 2%, to 98%. So we are now perhaps at a 90% range. So we still have a long way to go, but that's basically what the state of art or the general prevailing thinking is about. If we can improve that to 98%, then this technology probably will be a credible technology for deployment and for some real-world applications. We're not there yet, but it's closer. It's closer, let's put it this way.
But you use only the shape. You combine
oh, yes, exactly.
Yeah.
So in the case of shape, like you have all the range data, what do you think is the most challenging thing in the 3D data matching? I mean, is it because of sensor noise or because of...
It's actually data acquisition. People think that the 3D range surface will be invariant to lighting. And our good friends from the Notre Dame, through their experience acquiring those images, they basically say with the current 3D, 3D range image acquisition equipment, the lighting is very important. If there's an interference of lighting, then the 3D range acquisition will be very noisy and useless.
Well, what equipment do they use?
No, they're using, I think, RICO, some of the scanner type of things, you know. Yeah, I think the current state of art, people talk about the structured light, structured light from for the 3D, acquisitions, in the University of Washington, and some other groups are doing those. Well, structured light means that you have to, shine the lights on the face, right? If it's a visible light, you don't want to have a different shade there because that will affect your structured light acquisition. If even it's invisible light, you don't want to use laser. It will be harmful for the subject, right? So there are things you have to be careful. So unless you really get a mode to get a 3D surfaces, otherwise lighting will affect in one way or the other of acquisition. Yeah.
Sensor noise is actually
That's according to the person who do the data acquisition. That's their claim that lighting is still an issue there. Of course, then there's another problem. That the 3D surface means that the smooth surface is better, right? And the hair piece usually are not very good, right? And also beards. There's people with big beards, and that surface is very difficult to categorize. And so that makes the selection region very important. Maybe in the future we would have to exclude the mouth region because if a beard cover it, then the mouth shape will not be available in any sense.
Yes, the database doesn't cover the case where the training data has the beard and then the test.
Right, exactly. And also,
technical fail.
And in the acquisition, not all the surface points are acquired. For example, the eyes usually are missing, and some part of the the occlusions will also cause problem between the nose regions. And when there's a lot of people say, that for expression invariant, the ear is the best one, because no matter what expression, your ear does not change that much. The trouble is that most acquisition of a 3D faces, the ear is very difficult to get. You don't always ask people to show me your ears, right? And so, there are all these practical considerations.
So for instance, if in the training data and test data you have quick mismatch with training data maybe is all beers. When the tester does your technique.
We will fail miserably with this way. So that means the selection of the reliable sections of the face is very important. Once we have those kind of occlusion-based situations, then we'll impact on what kind of weighting we should use. For example, nose part is usually, unless you do a nose job, otherwise nose are less sensitive to either expression or to the coverage, right? You wear, unless of course you become a Santa Claus or you wear this Halloween, otherwise most of the time your nose is outside. Right. That, or the cheekbone, those parts usually are not covered by hair. So those are better. The eyebrow, it could be difficult.
So the research in this field has not addressed this mismatch issue.
Well, we just do not have enough training data, I guess. If we have a even larger set of training data, like tens of thousands with all these variation occlusions included, then I'm sure that the selection of feature, those things will gradually capture those. So this is just the beginning. I don't think this problem is ever is close yet.
Neutral versus no neutral. No measure.
Right, the neutral phase expression and those things, theory, we don't even know how to address it. Practically, it's very difficult.
Through that invariant transformation.
Well, invariant transformation is just one way of addressing this problem. It's just one feature. It doesn't mean that we should ignore other features. I'm sure there are other, even the differential invariant feature, we may have to use it. We just don't have time to explore those possibilities. So I think the contribution really is that we just give more options of features for you to select. We're not trying to say other features are not good, because we don't know.
So stepping up in the higher level, is the problem more in terms of the feature extraction or in terms of back-end?
I would say that the feature, it's really the invariant part that's more difficult. And I'm sure, the speech, processing people like you guys knows much better than these. Those invariants could be very, very difficult to address. But as I think the face recognition community can learn something from speech recognition community. Yeah, how to define the problem.
So probably for 80% of work, 80% of work is done in the back end. 20% work is in the front end. So I'm surprised in this area, maybe.
So I think that this is new in the sense that we are actually addressing the new features, because very few people actually look into that. Most people are trying to do the massaging of existing feature and do something. And here we actually provide fresh new feature available for people to choose from. They may not be the best. We may not want to use them, but at least they are new choices. Okay. Thank you. Appreciate it.